So I'll be recording my tutorials and posting them afterwards. And the slides should already be posted on Quarkus if you need them. So this is the first tutorial in ECE297. And for the first tutorial, I will be covering C++ templates and the C++ standard template library. So first, what are templates? Outside of programming, you might have already seen resume templates that you can download from the web, and you can fill in your name, experience, education, etc., and make the template your resume. And you can reuse one template for multiple people. And this is similar for generic programming. And today we're going to answer these questions. First, what are C++ templates? How can I write a function and a class template? And when should I write the templates? The idea for generic programming in C++ is to not constrain in C++. Generally, generic programming is a way to write code once that works for multiple types. For example, float, integer, char. And what can be templated in C++, we are going to cover functions and classes. And you can template some other stuff too that are not going to be covered. And you can go to the textbook for reference. First, function templates. Here are two swap functions. The first one, we are taking in two integers by reference, and we are swapping the contents in them. The second one, we're taking two doubles by reference, and we're doing the same thing. These two functions both are named swap. They do the same thing. The only difference is the type. The data type is integer versus double. So first question, will this compile? Why or why not? Can anyone? Who thinks this will compile? Who thinks it won't? So whoever thinks it will compile, why? Function overloading, because they have different signatures. So the compiler will call whichever one based on the parameter types. Now, if we want to implement the swap function for all data types, option one is obviously to write a function for each type that you are using. And in this case, it will only support the types that you want. And in this case, it avoids the user using the function to do swap on two types that don't make sense. But the negative is that you'll need to write a new swap function for each new type that exists. This is very error prone because it's a lot of copy and pasting. And if you need to change one code, you'll need to change all of them. If you miss even one of them, it could be a mistake. And it's hard to debug. So option two is to write a template where you can pass in any type into the swap function. The positive is that it supports all types that will compile based on how you code the function. And this avoids the reusing of code. But it could result in longer compile times because the templates are handled by your compiler. Here is an example of writing a template. The first line tells the compiler we want to use templates with the template keyword. Then in the bracket, we have the type name keyword. specifying the name of the type that you're using. This is a general name that you're giving to the type. And then afterwards, when the program is compiling, the compiler will search in the piece of code right after the template keyword, template statement, and replace the type name with whichever data type it's actually using. And in this case, the swap function will compile if you're passing in one single type for A and B. And this type must have the assignment operator defined because you're coding it in here. To use it, you can either, for example, we have two integers I and j. You can directly call swap with I and j, and it will work without issues. If you have two doubles, x and y, this is just another convention of calling it. You can explicitly tell the compiler to do double as the type and passing x and y. This will also work. Now let's consider these cases. We have two integers, two doubles, two chars, and these cases of calling swap. Who thinks case 1 can compile? Who thinks it doesn't compile? Who thinks case B can compile? Who thinks it doesn't compile? Who thinks case C can compile? Who thinks it doesn't compile? Who thinks case D can compile? Who thinks it doesn't? Who thinks case E can compile? Who thinks it doesn't? So for case A, because we have M and N, the same type, it compiles. Case B, because I and N are not the same type, it doesn't compile. Case C, I and J are integers, but we are explicitly calling double, so it doesn't compile. Case D, I and J are integers, and we're explicitly calling integer, so it compiles. X and Y are doubles, so explicitly calling char doesn't compile. And that's the answer. And one trick is that people will usually think that if you pass in an integer to a double, it works, but it doesn't in this case. Okay, now let's go into the first exercise. We want to implement a templated minimum function. For the minimum function, we're taking in two arguments, A and B, and we want to return the minimum value of those two. So let's go to this URL, and there are two exercises. Complete the code under exercise 1, and we'll be back in 4 minutes. You can test your code using the compile and run buttons. Anyone needs more time? Just exercise one. I'll continue. So this is the code that you should be writing. First, testing if A is less than B. If A is less than B, return A. Otherwise, either they're equal or B is less than A, return B. So when will this function compile? Yeah.
I guess if the page with the name here and all this is required. Compare the structure, multiple things together, or you can like do this here, comparing intermediate. It's not like defined.
Yeah, it will only compile when A and B can be compared. So if the operator less than is defined, because you're using the operator less than. If you're using the greater than, then it has to have the greater than operator defined. That's just how you code it. And the other condition is when exactly one type is used. So A and B must be of the same type. This is similar to swap. And when it's operator less than not defined, it could be something like arrays or something on the heap, like what you said. And that's it for function templates. Is that clear so far? Let's do class templates. What would you template inside a class? Inside a class, there could be member functions and member data, and you can template both. For example, a template array class can store an array containing different types of values. Same for the linked list or binary search tree. The example we'll be using in this tutorial are pairs. A pair is used to store two pieces of data together, so it will contain a first object and a second object, or a key and a value. So you should have already seen this in 244 in binary search tree. The binary search tree nodes will store a key and a value. Both can be of different types. Could be a key that's a string or and a value of integer or anything like that. So let's write a pair class that can store two arbitrary pieces of data together of any first type or second type, and which can be used to insert into a binary search tree. So what we want is two members, first, second, and they can of the same type, of course, and we can instantiate with different types of the first and second. And here's the implementation of the pair class. Similar to functions, on the first line, we have the template keyword. And inside the bracket, because we have two different types, so we're defining two different type names. In this case, we're calling it first T and second T. Then the class name, the class constructor, setters, getters, and the private data members. One thing to watch out for is that all of the definitions for the templated class must be all inside the header file. So you cannot split the code into .h or and .cpp file. You have to have all of the definitions together inside the header file. This is because the compiler must be able to find whatever it needs to replace. If it's split into the .cpp file, the compiler won't be able to find it. So the actual implementation will look like this. For the constructor, we're assigning first value to first, second value to second. For the setters, we're doing all of the implementations in here and etc. Then to use it, we can use the constructor of the pair. So in this case, we need to specify the two types when we're constructing the pair. So pair, the two types, and then the constructor having the two values. Then we can use the getters and setters. This should be pretty straightforward. And I'll move on to the first demo. Read the code and see what's happening. So we have a templated max function That's returning the maximum value between A and B. And in the main function, we are calling it for 3 times. One for double, one for integer, and one for double. And we're outputting the 3 results. Let's compile. Okay, there's a compile error. We can see that these notes are just notes to suggest what might be the error, what might be the cause of the error, and the error message is the actual thing we need to look at. So if the compiler gives you a lot of messages, just don't panic and just look for the error. So in here, it says on line 17, there's no matching function for call to a maximum of double reference and an int. And that's line 17. Double D equals to max x and 2. So if we go to line 17, it's this line. So the compiler sees that the x is a double, but it thinks 2 is an integer. So what we need to do in this case is to make the 2 explicitly into a double by doing this. And to the terminal again. Now the compiler is gone. Let's run it. We have the right values 1.2, 3, and 2. 1.2, 3, 2. Okay. So that's it for demo. General tips for writing templates. The first tip is to don't write templates, especially in this course, because writing template can be complex and the template errors can be very hard to fix and overwhelming for beginners. But you should be using templates written by other people that are already existing in the standard template library or some other library you can find online. But if you do write templates, just make sure that you are writing the code for one single type first. Make sure the code works, then convert it to a template and test it again with different types. This will avoid this kind of style of writing code will avoid a lot of debugging time. And yeah, that's it for the first half. We can have a short break and we can come back at 4:40 for the second half. Recording. Okay, let's start the second half. The standard template library or STL. If you write C++, you will need to use the STL starting from some point in your career. Why should I use the STL? And we are going to be using the SCD vector as an example. Why do we use the STL? It could be difficult to write your own templates, but using templates that are written by other people and refined and optimized year by year is much easier and more productive. The STL has a lot of things covered that you can imagine, like the swap function, the sort function, the pair class, the minimum function, and so much more. The containers library from the STL from the name, it has many containers defined. For example, the list is a doubly linked list of some type that's templated. A vector is a dynamic array of elements of some type, also templated. So for example, a vector of double is a dynamic array that stores doubles. A list of string is a linked list that stores strings. Why do we want to use std vector instead of arrays? If we want to read integers from the user to an array until the end of file, so you don't know how many values you're reading in until you're at the last element. Then do some work on the array. So you don't have any idea of how big of an array we should be allocating when we are allocating the array. We only know until after all of the input is read. We could use a linked list, but if we want to access any element in the array, it will be O(n) time because you need to start from the head and traverse through the linked list. A better solution is an array that can grow dynamically in time whenever you need it. And it takes O(1) time to access an element using its index. And that's vector. For std vector, it has the operator square brackets, so you can access any element like how you would access in an array. You can read it and set it. The pushback function inserts a new element to the end of the array. And because the array grows in size, if you need to know the size at some point, you can just call the size function. So the code to accept integer input into a vector is clear now. So we first create a vector of integers. Using this. So first you need to include the vector library, the vector header in the STL. And we can specify that we're returning a vector of integers from a function. And here it calls the default constructor of vector of integers. And this will create an empty vector of integers. So then we can read in the values from the std input until the end of file. And we push back the value each iteration into the vector. Then at the end, return the vector. Pushback inserts a new element into the vector and will grow the vector in size. And now this is exercise 2. We have what we just saw as get integers from cin. Now we want to use a for loop to print out each element in the vector. We can use the operator square bracket and size. And let's go back to the IDE and complete the code under exercise 2. And we'll be back in 4 minutes.
Yes. I just didn't know. Yeah, I don't think it's not large.
Anyone needs more time? Okay, let's continue. So here is what your code should look like. We have the for loop that goes from I equal to 0 to 1 less than integers dot size. And then we output integers I, square bracket. And this code will separate them by spaces and a new line at the end. How are vector implemented behind the scenes? So say we have the default constructor of vector int creating a vector of initial capacity of 3. We're assuming the capacity is 3 in this case. So initially it has a size of 0 and no elements in the array. And we have the array inside the integers object of a size 3. Now at the first pushback, we're reading in the 1 from the input, and we're writing the 1 into the array, incrementing the size. Then the second pushback, 3, increment the size. Third pushback, 8, increment the size. Then at the fourth pushback, we are exceeding the capacity of 3. So what vector does is that it creates a new array of size capacity times 2, 2 times size. So now we have an empty array of 6 elements. It copies all 3 elements into the new array. It deletes the old array and points to the new array. So now we have a new array of capacity of 6. Then for the fourth pushback, we are writing in the fourth one and incrementing the size. and until the end. So every time when we exceed the capacity, we are doing capacity times 2. And the complexity of the vectors algorithm with pushback is on average 1. And this is because we are always using times 2 on the capacity. And if we have a sufficiently large number of n, on average, the complexity is 1 because the increment of capacity is few enough that is negligible for a large number of n. Hope that makes sense. And this is why usually starting from an empty vector and then pushing back could be a bit slower than just allocating a big vector and then just setting each one of them. It just depends on your design choice after all. And we have 3 different constructors for vector. First one is a default constructor of size 0. The second one is specifying the size with values unspecified. You can just allocate a vector of size 10 and then just assign each value independently. Or the third one is allocating the size and setting the values. This makes sense. Any questions? Now, vectors versus the C-style arrays. Say we have 2 arrays A and B that are created by new of size 10. And we have 2 vectors of size 10. We can access the elements the same way. And we have to delete the 2 arrays created by new at the end. And let's look at these 2 lines. What happens when the program executes A equal to B? Yeah. It's actually going to work. Yeah. A and B are pointers to arrays. So when you do A equal to B, you will be pointing A to B's location in the stack. So whatever in A is lost, and that's a memory leak. But your program is still going to work. And what happens when you do V1 equals to V2? Anyone? When you do V1 equals to V2, it will be a deep copy. So V2's elements are going to be copied to V1, and they're still going to point to different locations in your memory. So when you, even after this, even if you change V2, it's not going to change V1. But if you change B, it's going to change A. Do we need to delete V1, V2? No, why?
Probably when you include vector, probably the vector class itself is so when you like when this everything made up gets finished all the time also.
Yeah, vectors have a destructor. And if you are creating the vectors like this, the definition is stored on stack. So when this function ends, it will call the destructor and clean up after itself. So the idea is to avoid pointers and let the STL do the cleanup for you as much as possible. And by the way, memory leaks are checked in your milestones in the automap. in the auto marker. So if you have memory leaks, it's going to deduct marks. So definitely that's something you need to avoid. One negative for the vectors is that the operator square bracket doesn't create values and it does not check bounds. So if you read in from an out of bounds index, your program is still going to run. You're not going to get any compile errors, and your program won't crash if you read from an out of bounds memory. And if you set something out of bounds, your program will crash. And if you want to debug something like that, you can use the debug check configuration to do bounds checking. But debug check will make your program run more slowly. And I'll show this afterwards in the demo. If we're doing something like this, if we push back the first value into an empty vector, we can set the first value, but if we want to set the second value, the program is going to crash. Because you're trying to write into somewhere that you shouldn't be doing. The algorithm complexity for accessing data with the operator square bracket is 01, because it's just accessing inside of an array with index. And here, I'm going to do the second demo. The first one, I'll show why we need to use debug check build to the If you want to use VS Code on the UG machines, you can just call code dot, and this will open the current folder. I'm just showing this to you. You don't need to use it, just in case someone wants to use it. So in this case, the code that we are running is this. So we are including the vector, and in the test vec, we're defining a vector with size 100 and initializing all of them to 20. And then for the for loop, as some of you might already see, it's accessing out of bounds memory, but we are going to leave it for now. And we're adding the index I to whatever is initialized in the vector. So after this, everything in the vector should be 20 plus index and see out the current value. So in the VS Code on the UG machines, you can access the makefile here. You should be changing the configuration, but because the makefile is not set up properly here, I'm not going to set it. And the build target, I'll set it to vec_bad, and the launch target to the same thing. And here is build. So we can see that there's no compile error, even if we are accessing out of bounds memory. Let's run it. You can see in the terminal here, everything is making sense until 100. It's outputting garbage values, but the program finished executing to the end. And this could be a source of error that's very hard to debug in your own code. And your compiler and your program are not helping in this case. So what I'm going to do is to make clean and make with configuration equal to debug check. Actually, I'll show you the 3 configurations. So the first configuration is release. And these are the compile flags. And if we run this, this is the same code that's not desirable. And let's do make debug. So for debug, the compile flag is changed from 003 to 00. And if we want run this, it's the same output. Let's make clean and do debug check. You see that the compile flag is way longer than before. And F-sanitize are the flags that are used for memory checking. Now let's run this. So the program outputs all the way to 99, index 99, which is correct. And then when it tries to read from out of bounds memory, it's giving an error with trying to read out of bounds index 100 in a container that only holds 100 elements. And it tells you here that it's a vector. So that gives a hint. But still, it doesn't give you the line number or the file that you should be looking at, but this only gives you a hint of the index that you're trying to access and the container, the size of the container. So that's why the debug check flag is returned in some cases. And the last demo is on the speed. So we're going to do 3 comparisons. The first one, release versus debug check. Which one do you think is faster than the others? And which one do you think is the slowest? Release is the fastest, and which one is the slowest? Debug check. Yeah. Because intuitively, debug checks for more things. Yeah.
So using the vote check, what's it do? Like
It's checking for memory leaks and out of bounds memory access. Like whether you are accessing memory that you are not supposed to do. And it's generating a report on memory that you can use some of the other tools to visualize. So the next one is vector versus arrays. Which one do you think is faster? Yeah.
arrays.
Arrays. Do you think they are about the same?
Yeah. About the same. They're both in the same type of thing.
Yeah, depending on how you code it. Could be about the same. How fast is Python versus C++? C++ is way faster. Let's see it. So in this folder, we have a .cpp file. And we have a very large size of n. We can either use a vector or an array of size n, and then we do something with it. Then we have another file that's a Python file, which is doing the same thing. So the first thing we want to see is the compiler optimizations, the compiler configurations. And let's first do a make configuration release. And let's test vec versus array speed. So how to read the output from the time command in Linux? The first number is the user time. The second number is the system time that you don't need to care about. The third one is the wall clock time. That is the actual time it took to execute the program. So the first 0 is the time in minutes. The second 0.47 is the number of seconds. So it took 0.47 seconds. Let's make clean and do a debug. Time. 1.06 seconds. But that's about twice as slow. And let's make clean again and do a debug check. You see the speed, 6.89 seconds. That's about 14 times slower than release, which is why when we are doing anything with speed, with time, we always measure the release configuration. Make clean again and back to release. We have this time. And let's compare vector versus arrays. Let me comment out vector and uncomment array. Measure. .44. So they are very close. And actually, in this case, they are the same. They're supposed to be the same. The difference is only depending on the machine load at this time. And because this time is short enough, it doesn't really matter the difference. Let's go back to vectors. And let's find the Python time. Yeah, as you should already be feeling, this is even slower than debug check. .49 seconds. But the Python code is shorter, so there is a trade-off between the runtime and the convenience coding. Productivity, yeah. And that's it for today's tutorial and demos. So if you need to learn more about C++ and the STL, you can go to the textbooks or online. C++reference.com and Google are very good resources for researching about the STL and researching about what container you should be using for your milestones. And yeah, that's it for today's tutorial. Thank you.